This is reading week 12 for Physics 2212. In the first video this week, we talked about inductance. Inductance means that the B field, which changes with time, can produce an EMF in a set of conducting loops such as a coil. We then looked at an example with a solenoid in a circuit. Something that we already knew was that the equations here would involve time, since we started with an open circuit and then closed it. This means the current was time dependent, and in turn, the magnetic field, magnetic flux, and EMF were all time dependent as well. Something that I learned from this video that I didn't know before was that we can further simplify the equation for the EMF by replacing the inductance with a capital L. In our equation for EMF, the inductance was mu naught ns squared pi rs squared divided by ls. I did not know that the electric field for the solenoid would oppose the electric field for the EMF as seen in the picture. In the example from the previous slide, we can apply the loop rule first by simplifying the circuit to better visualize the simple situation. So we have the EMF of the battery on the left and the EMF of the solenoid on the right. We can then just plug in the equation that we found for the EMF of the solenoid, which we subtract from the EMF of the battery, and this is going to equal 0 by the definition of the loop rule. We then looked into the example on the right, which we could derive an expression for the current I using the loop rule again. We also learned about the time constant, which is L over R, and this is the time it takes for something significant to happen to the circuit. I found the idea of the time constant to be a little confusing and was curious about what they meant by something significant happening. So I found a couple of resources that helped explain it. I found some particular articles from electronics tutorials and the All About Circuits website that helped me understand this a little better. Basically, to calculate the time constant of a circuit, you need to find the amount of time it takes for the voltage or current values to change approximately 63% from their starting values to their final values in a transient situation. I found it helpful to look at equations for this and how it can be represented in different ways. Next, we talked about Gauss's law, both for electric flux and magnetic flux on a closed surface. And the electric flux on a closed surface differs from uniform electric flux because there's a circle on the integration sign, which means that we are integrating over a closed surface. And a closed surface just means that there is a volume inside of this shape that is separate from the outside. And this also means that the normal vector will always be pointing outward from this shape or object that we're looking at, but it will change based on which surface you're looking at, which of the faces. Gauss's law for this situation is equal to Q enclosed, the charge on the inside of the closed surface, over epsilon naught. And then when we applied these same ideas to the Gauss's law for the magnetic field, we found the magnetic flux over the closed surface should be 0 because there are no magnetic charges that exist. Gauss's law describes what an electric field will look like due to an unknown distribution of electric charge. I'm studying environmental engineering, which often assesses humans' risk and risk to the environment too. And one of these risks to humans, which in turn to the environment, could be electric fields, and exposure to power frequency has been linked to human health concerns fairly often. And it's not only noted in the United States, it's been noted across the world. And this may lead us to look into some alternate sources of power or maybe coming up with some more humane practices for electric fields.